Hello everyone. Today's lecture is about the label propagation. So let me ask you a question. So given a network with labels on some nodes, how do we assign labels to all other nodes in the network? So which is related to the node classification. So we already have some ways to do that using graph neural networks and node embeddings. I'm asking about do the classification on the direct graph space. For example, in a network, some nodes are fraudsters and some other nodes are fully trusted. And how do we find the other fraudsters and trustworthy nodes using the graph structures only? So without neural networks, I mean. So this is pretty similar to what we had before during the lecture, and colors denote the class labels in gray nodes mean the unknown labels. So given labels of some nodes, so we can predict labels of unlabeled nodes. So this is called semi-supervised node classification because we leverage the structure of the graph data, but we just don't know the labels of unlabeled nodes. So we have several key assumptions about it. So we assume correlations exist in the network. So when similar nodes are connected, we assume that some correlation is involved in the construction of the hedges. So by having the assumption, many people have proposed the collective classification methods. The idea is that we can assign labels of the unlabeled nodes by utilizing the graph structure itself and labeled nodes all together. So again, we use not only the graph structure but also labeled nodes, so which is called collective classification. So we will introduce some traditional approaches such as relational classification, iterative classification, belief propagation. So they're all based on non-deep neural networks and fully connected layers. So, but it is important to understand the traditional approach. So this is what we just talked about in the previous slide. We assumed that there exists correlation in the network. So individual behaviors are correlated in the network. So correlation is that from the correlation, we usually expect that the nearby nodes have the same color. So what do you have to measure the correlation? maybe Pearson's correlation is one of the easiest way to measure the correlation. What else? Maybe some statistical test to do that, to see the nearby nodes are statistically different or not. We have many different ways to do that. So depending on your assumption about the correlation, your future methods could be different, but in this case we just use the term correlation to indicate that nearby nodes are likely to have the same class label. We have two types of dependencies in networks. This may explain how the correlations are created. So first one is homophily. We sometimes talked about homophily during the previous lectures. So homophily means that from the individual characteristics, when they have some common characteristics, it is likely to create social connections. Influence is slightly different. So from the social connections, when something happens, so the same information is propagated in their individual characteristics are modified or changed or affected. So they are different dependencies in network. So the upper square means that because of the dependencies in the bottom boxes, the bottom squares, the rounded squares mean that they jerk up the previous causes. So from the influence, so for example, you can find many use cases of the jerked up influence. So when you go to the social media in Instagram, Facebook, and Twitter, so you are exposed to some news articles when you watched the news, and you have used some attitude toward some story or some policy or some accident could be changed, is affected, right? So which is called you are influenced by some news articles or famous people, and you can propagate that information, and it may cause the change of your friends thinking, right? Homophily is different, right? So from the individual characteristics, for example, when you take the machine learning with graph class, and you have new social connections, so there are different dependencies. So let's focus on homophily. So it is the tendency of individuals to associate and bond with similar others. So birds of a feather flock together. So this is the famous phrase to explain homophily, and it has been observed in the vast area of network studies and based on the variety of the attributes in gender, age, the organizational role. So the tendency, the similar tendency generates the edges. So another example could be found from that the researchers who focus on the same research area are more likely to establish a connection, debating at conferences, interacting in academic talks. So we establish a connection. This figure shows an example of homophily. And this is one of the online social networks. And the nodes represent people, and edge mean friendship, and node color represents interests such as sport and art, etc. So in this graph, as you see, people with the same interest are more closely connected due to the homophily. So they share the similar characteristics and they are likely to be connected. So it is very important to visualize if possible. And so you need to see how the edges formed. So by looking at the colors and their distribution, we'll expect to the edges. So you see that homophily dominates in this graph formulation. Meanwhile, the influence causes the individual characteristics. So social connections can influence the individual characteristics of a person. So for example, I recommend my musical preferences to my friends until one of them grows to like my same favorite genres. So this is the example of influence. So then how to leverage the correlation, the dependency to help predict node labels. So in this case, we assume that homophily, we try to utilize homophily for improving node classification. So label is done none, and there in that case the colors are used for the graph. So in this example we have 4 nodes are known, the others are colored the gray, so we don't know about their labels. So similar nodes are typically close together and directly connected in the network. That is our assumption once again. And guilt by association, if I am connected to a node with the label X, then I am likely to have label X as well. So in your favorite web page, in malicious and benign web pages, you are likely to find the links are created from the similar nodes. So classification label of node V in network may depend on the features of V in labels and in their neighborhoods, the features of the nodes in the target V's neighborhood. So we don't know about the label of the node V, but instead we know about the features. and these neighborhood, so we are able to find their labels. Could be not. And we also may expect we can observe the features of the nodes in node V's neighborhood. So given the graph and few labeled nodes, we try to find the class labels of the remaining nodes. Our assumption is that there is homophily in the network. So this is more formal definition about the task. So we try to simplify the task. For example, so we have only two kinds of classes. So class 1 and 2, and they are unlabeled, needs to be classified. Our goal is to predict the unlabeled nodes are likely to be class 1 or class 0. We try to predict. So we have multiple ways to do that. We have 3 simple list classifiers for them, particularly so in a semi-supervised setting by leveraging homophily. So intuition is the same. So we try to use the probabilistic framework. The homophily provides us to the chances to utilize Markov assumption. So Markov assumption is that the label of the node V depends on the labels of each neighborhood. So Markov assumption is it depends only conditional to the previous observation, right? So in this case, we can apply to the graph setting. So it depends the labels of each neighbor. So probability of the label V depends on the labels of each neighborhood's the label. So by having this assumption, so we can compute the probability about the class label 0 for the node V or class label 1 for the node V. So we have 3 steps in this case. First one is a local classifier, and second one is the relational classifier, and third one is collective inference. So by using local classifier, so we can assign a label, and then we can also utilize correlations from the homophily, and we can put another class label, and we can propagate correlations throughout the network. So each one may predict the class labels, but when we utilize these classifiers and inference at the same time, I mean the sequentially utilize this, we expect better performance. So let me explain these steps one by one. So local classifier is to assign initial label for the unlabeled nodes. It predicts labels based on the node attributes, features. So we assume that their attributes are known. So by utilizing these existing classifiers such as SVM and logistic regression, and we can predict the labels. So in this stage, we don't use network information. And then next step is to capture correlations. So this classifier learns a classifier to label one node based on the labels and attributes of each neighbor. So in this case, we use network information. And I will give you more details about it. And third step is that the collective inference. So we propagate the correlation. We apply relational classifiers to each unlabeled node iteratively, and we keep propagating the temporal prediction from relational classifier until convergence. In this case, network structure also affects the final prediction. So before we move on to the details and examples, so once again, let me give you the problem setting. So in this case, the notation YV is the labels on the node V. So in the individual below, the gray means the unlabeled node, and node V has a feature vector, so we call FV. And labels for some nodes are given. We put one for green and one for red. And task is to find the probability of P of YV. So this is YV given all features in the network. So let's move on to the detail. So for the classification, so we talked about these steps, right? The local classifier and relational classifier and collective inference. So for the relational classifier stage, we need to initialize for the unlabeled node. So we have two different kind of nodes, right? So labeled nodes and unlabeled nodes. For labeled nodes, we initialize label of node V with the ground truth label because it is known. We still utilize the known information in the training data. For unlabeled nodes, we initialize with the 0.5 and update all nodes in the random order until convergence. And I will give you more examples. So you may notice that in this case, the local classifier the relational classifier may utilize a local classification or not. So you can utilize the local classification for unlabeled nodes in this case. But if the attributes are not available, we initialize as 0.5. So that is the difference. So I think it is quite confusing to understand. So, but in this case, we assume that we don't have the features, so difficult to predict the labels from the local classifier. So we initialize the labels of the unlabeled nodes as 0.5. In this case, we assume that, where's my mouse? In this case, we assume that when the value is larger than 0.5, we put the label 1. Otherwise, we put label 0. I mean the class 1 and 0. The class label it depends on the value of this variable y.